The following is part of a college course based on the textbook Horizons: Exploring the Universe, written by Michael Seeds and published by Thomson Brooks Cole Publishers. The universe is beautiful. Thousands of eyes look into the sky every night to catch a glimpse of the wonders that it paints with light. But this light does more than create amazing vistas. It can tell about the nature of our universe. Using the process of spectroscopy, in which the colors mixed in a beam of light are separated and analyzed, astronomers can uncover the secrets of the myriad sources of light that their telescopes can capture. Without the subtle data carried by the light, our understanding of the universe would be limited to only the beautiful images it creates.
Spectroscopy, I believe, is the most fascinating part of modern astronomy because it enables you to tell something about the nature of the objects in the universe in much detail without going there and touching them. Because of spectroscopy, you can tell how hot a star is, how big it is, what mass it has, what the chemical composition is, and you can even tell how far it is away from us. And all the information comes from spectral lines in the spectrum of stars.
Deciphering mysteries of the universe with spectroscopy requires a basic knowledge of how light is created and how it interacts with different types of matter to generate unique spectra. To unlock the secrets of the infinitely large, we must start with an understanding of the infinitesimally small, the atom. In this model, the atom has two major components. The first is the nucleus, the central core of the atom, which is composed of protons, which are positively charged, and neutrons, which are neutral. The second component is the cloud of negatively charged electrons, which surrounds the nucleus. The number of protons in the nucleus of the atom determines what chemical element it is. Hydrogen has 1 proton, carbon has 6 protons, neon has 10, and so on. An electron can orbit the nucleus of an atom only at specific distances known as permitted orbits. The number of protons in the nucleus determines the arrangement of these orbits. Here we have an illustration of an atom of hydrogen, one of carbon, and another of neon. The combination of orbits is unique to each element and can be used to identify them, much like fingerprints identify individual humans. No two elements have the same combination of permitted orbits.
There's a very simple model of the atom that was created by Niels Bohr. It's a model, but it is useful in explaining certain phenomena with regards to how light interacts with matter. It's not very realistic in other regimes, but it's useful in this application. You can imagine the electron as orbiting its nucleus. But the difference between an electron orbiting an atom, or a nucleus of an atom, and a planet orbiting the sun, for instance, is that an electron cannot take on any orbit it wants. It is only allowed very specific orbits.
Let's consider the simplest atom, hydrogen, which has just 1 proton and 1 electron. Although the electron can only reside in one of the permitted orbits at a time, it is free to jump between them. To understand this concept, imagine a multi-story hotel. The floors of the hotel are the permitted orbits, also referred to as energy levels, because it takes a specific amount of energy to get to that level. When the electron checks in, it is assigned the first level. This is the electron's normal or resting energy level, what scientists call the ground state. To move the electron between the ground state and higher energy levels, the atom must absorb energy either through collisions with other atoms or by absorbing the energy of a photon of light. An atom that has absorbed energy in this way is said to be an excited atom.
So an electron can be transferred to a higher energy state or a larger orbit about its nucleus by giving it just the right energy. It can get that energy in various ways. For instance, a collision can get it up there, but another way of giving it that energy is with light, with a photon. But the photon has to have exactly the right energy. If it has too much, the electron will just let it pass right on by. It has to have exactly the right amount. And if it does, the electron will absorb it and will use that energy to put it up into a higher energy state.
For instance, in a hydrogen atom, only a photon of exactly the right energy will send the electron to the second level. It takes a different, larger amount of energy to move the electron from the ground level to the third level, and yet more to move it on to the fourth level, and so on. Since energy, wavelength, and color of a photon are all related, we could also say that only a photon of the correct wavelength will excite the atom, or alternately, only a photon of the correct color will work. All these statements say the same thing. There are thus several different wavelengths, colors, or energies of light that can be absorbed by the electron, each moving it to a different, higher level.
Once the electron takes that energy and uses it to go up to the higher energy state in a larger orbit, it's immediately going to turn around and jump right back down.
If the electron jumps directly back down to the ground state, it releases the excess energy as a photon of exactly the same energy it had absorbed. But like an elevator, it can stop briefly and even linger a while at other floors along the way instead, emitting a less energetic photon at each stop. Since the energy levels of each type of atom are unique, the photons an atom emits during this process have unique energies or colors. By analyzing these colors using spectroscopy, we can distinguish what types of atoms are present. Spectroscopy can determine not only the chemical element emitting the light, but also environmental factors, such as the temperature and density of the atoms. To appreciate how astronomers do this requires an understanding of the different types of spectra astronomical objects can emit. In the mid-18th century, a German scientist named Gustav Kirchhoff identified 3 different types of spectra through experiments as he burned chemicals in his laboratory and observed the light they emitted. His classification now bears his name as Kirchhoff's laws. The 3 types of spectra Kirchhoff observed are called continuous spectra, emission or bright line spectra, and absorption or dark line spectra. The easiest to understand is actually Kirchhoff's second law, the emission spectrum. This deals with the absorption of radiation by electrons in a low-pressure gas, which re-emits that radiation at different wavelengths. An emission spectrum is observed as bright lines in the spectrum. These are caused by the electrons emitting photons at specific wavelengths as they move toward the ground state from higher energy levels. Our modern world is filled with examples of excited atoms whose electrons absorb and re-emit photons. The best are neon signs, where electricity is passed through a tube of gas, exciting the atoms in the gas and providing energy to the electrons. The electrons of the excited atoms cycle back and forth between lower and higher energy levels, emitting photons at wavelengths that are specific to the type of gas inside the tube. The different gases in each tube emit photons at unique wavelengths, giving each a specific color, and, viewed through a prism, a specific spectrum. This is the signature of the element. Emission spectra are the fingerprints of the chemical elements, each with a unique emission spectrum. Since emission lines reveal the chemical composition of a gas through their unique signature, astronomers take the known emission spectra seen in the laboratory and compare them to the ones they observe astronomically to determine the composition of the source. Kirchhoff's first law deals with the continuous spectrum. As opposed to emission spectra, which appear as bright lines at specific wavelengths, continuous spectra are produced by an object that gives off light at all wavelengths. For example, a horseshoe is being heated in a forge. As it heats up, it changes from dull red to brighter orange to brilliant yellow-white as the atoms become more excited, causing more collisions and radiating photons at shorter wavelengths. So the hotter the object is, the brighter it becomes, and the higher energy photons it will emit. But it also radiates photons at all the other wavelengths because the atoms are so crowded and interact so forcefully that they produce light of every color. Each atom wants to give off light at its own specific energies, but the energy levels are blurred. A solid, liquid, or dense gas excited to emit light will radiate at all wavelengths in this way and thus produce a continuous spectrum. The peak or brightest color of the spectrum indicates the temperature of the object. The value of the continuous spectrum to astronomers is that it easily reveals an approximate temperature of a dense gas. However, unlike the emission line spectrum, it does not reveal the composition of that gas. The third type of spectrum identified by Kirchhoff is the absorption or dark line spectrum. This occurs when a cold gas is between an observer and a source of continuous light. The gas absorbs the light that has the correct energies to boost its electrons to its various energy levels. All other light passes through. By the time the light gets to the observer, those energies absorbed by the cold gas have been removed and appear as gaps in the spectrum. Instead of bright emission lines at specific energies, absorption spectra show dark lines where energy is being absorbed by the atoms. Stars produce absorption spectra. The surface of a star is cooler and thinner than the gas underneath. The light from the hot, dense gas inside a star will produce a continuous spectrum, and the cooler gas above it will absorb specific wavelengths of that light, which appear as gaps in the underlying continuous spectrum.